Okay, so let me start this session by introducing myself. I am Moina Ghosal. I am a TA for this course, which is entitled as Fundamentals of Spectroscopy, which was instructed by Professor Sayan Bakshi and Professor Anirban Hajra. And this is questions regarding assignment questions regarding week number 12, where I'm going to explain some questions regarding fundamental spectroscopic techniques, and which will be beneficial for you to do your assignments and related questions. So if you have seen the lectures given by Professor Shan Bakshi and Professor Anirban Hajra in YouTube, and then you can, if you are going to solve questions, then it will be beneficial for you, and you will see how I am addressing each questions. That will also help you to build up your knowledge. Okay. So before beginning the session, just like previous cases, at um, just like previous cases, I am just telling about previous week's assignment, what we have taught. Mainly, I have discussed about EPR spectroscopy. Yes. So EPR, I have discussed about EPR. Okay. What is EPR? Why? What does it stands for? It stands for electron paramagnetic resonance. Okay. So it stands for actually electron paramagnetic resonance. Just before this topic discussion, in week 10, I have discussed about NMR spectroscopy, which is nothing but nuclear magnetic resonance spectroscopy. And in this week, in the week 11, in the previous week, we have discussed about EPS spectroscopy, which has the following condition that to be EPR active, you need to have one or more unpaired electron. Okay. So if your system has one or more unpaired electron, then it is supposed to show EPR signal. Okay. And then the application of this EPR in predicting organic reaction involving free radicals also proved. Why? Because in some organic reaction, like suppose you, if you have gone through Reimer-Tiemann reaction, okay, Reimer-Tiemann reaction, in such reactions actually what happens, that it goes through an intermediate which is like this one, okay, CCl2 dot dichlorocarbon. Okay, so it is a what to say, unpaired electrons are there. So from that, since it contains unpaired electron, then you can easily get paramagnetic signal or EPR. Okay, so in such reactions where there is an intermediate state, okay, and then it was discussed that for Reimer-Tiemann kind of reaction, suppose in this case CCl2 dot here, just like in this case. So in the reactions in which the intermediate is some free radical, okay, suppose methyl radical, ethyl radical kind of thing. So in that case, since they contain unpaired electron, so you can easily detect them, okay, through EPS spectroscopy. How? Because these intermediates will also EPS signal. But if there is no unpaired electron, they will not show any kind of EPS signal. Okay. So then there was a discussion on how, on which things the intensity of the peak depends. Okay, So it was shown that it depends upon the concentration of free radical or paramagnetic compounds. Okay, what is the concentration of this free radical or this paramagnetic compound? Upon this, the intensity of the APR peak depends. And also there was a discussion on sensitivity and width of the peak and the requirement for differential plot. Okay, so it was shown that the sensitivity is upon almost 10 to the power 13 minus 13 mole for free radical. Okay, and the width was shown that the width is almost equals to 1 megahertz. So you can just think of that how much broad is the spectrum for it. Okay, how much broad it could be. So from this discussion, this could be like from this could be like a APS spectrum. Okay, but since it is a very broad spectrum, so it will be very difficult to get the maximum position. Okay, for broad spectra, a range of value will be the maximum. Okay, so like since suppose this is the spectra, and then this will be maybe your maximum value, this may be your maximum value, this may be your maximum, you don't know. So for that, people have started taking differential spectra. Okay, why? Because up to this limit, this is positive slope. From this is negative slope. And at the extremum point or maximum or minimum point, the first derivative is zero. Okay, so if you plot like this, then from your zero position, you can easily determine what should be your maximum value. Okay, then there was a discussion on the experimental and theoretical basis of G factor. Okay, so from G factor, it was shown that G has a value of 2.002 like this for theoretically, and if you are going through experiment, it will go like 0.003. Okay, will be a accuracy, and this is the experimental. But all these results come from if you consider no spin orbit coupling. So this G factor that comes like for 2.002 for theoretically and experimental, it is coming 2.002 plus minus 0.003. This considers actually no spin orbit coupling. If you are considering spin orbit coupling, then the scenario will be little bit different. What different? Because then there will be the factor will be like Landé G factor. Factor will come as Landé G factor. What is Landé G factor? This is a gate formula. I have discussed that in the previous lecture, previous live session. That what is Landé G factor and how is it is actually varying. Okay. Then yes, what I have told you that is written here. If you consider spin orbit coupling, then your normal G factor will not be there. It will come like Landis G factor. Fine. Then it was shown that for hydrogen atom, only one line is expected, but it shows two lines. Okay. So for hydrogen atom, in EPR I have shown you alpha state will be the higher in energy than the beta state. Just like I am writing here, it is a beta, this is the alpha, so you expect only one line here. Okay, but it is shown actually that it is two lines are expected, two lines actually observed. Why? Because in that case you need to consider the electron which is present in the hydrogen. Okay, so hydrogen electron is present in s orbital, and if s orbital electron, and I have so told you that if there is an electron present in the s orbital, it can interact with the nucleus, and this will give you hyperfine structure. Okay, now why s orbital? That was also discussed, because if you draw all other orbitals, only s orbital will be there, at for which at the nucleus the electron density is non-zero. Okay, if you take p orbital and d orbital, there will be a node around around the nucleus. Okay, but it is only s orbital which will have a significant value of non-zero value of wave function near the nucleus. So that's why s orbital electrons will actually interact with the nucleus, and that will give you hyperfine interaction. Okay. Now coming to the main point, that for hydrogen, so there is an interaction of electron with the um, electron with the nucleus. Okay. Now for new hydrogen, you know, Mi is nothing but this I is half, nucleus being quantum number half. Okay. So Mi could be plus or minus half. Okay. So four states could be possible. For E beta, with mi equals to plus half, mi equal to minus half, these two states are there. For mi equal to minus half, plus half, two states are there. Then it was shown that the condition to for transition is delta mi should be equals to 0. That means from mi equals to plus half, it can only goes to mi equal to plus half. Okay, so so it was shown that for this case, this is minus. Suppose I remember actually, this should be, you can, if you put this value, then you will see which energy will be lower. Okay, so from one transition from here to here, another transition from here to here, two transitions will be only possible, and only two lines will be there. And the difference between this peak, so this is the peak, okay, and the difference will be A. What is A? A is called hyperfine splitting constant. Okay. Yes, also discussed that what is hyperfine splitting and what is hyperfine splitting constant. Then there was discussion on the finding the ESS spectra for CH3 radical, and there it was shown that four lines are present in the ESS spectra. Okay. So in that case, it was shown that four lines are present in the CH3 dot radical, CH3 radical, and how these four lines are present, because you know three hydrogens are there. Okay. So the lines will be divided into 1 is to 3 is to 3 is to 1 ratio. Okay. And why this will be four lines? Because if you go like this, then it will be divided into four parts. Okay. Plus 3 by 2 minus half plus half, like that. And four transitions will be allowed during this, so you will get four lines. Okay. So if you have any confusion upon this, you can see my previous discussion where I have discussed about all these topics. So for methyl radical, it can be shown that unpaired electron resides 14% time on hydrogen atom, because it was shown that there is a dependence of this hyperfine splitting constant A on rho. A is actually directly proportional to rho. Now what is rho? Rho is nothing but unpaired electron density. Okay. So it was shown that it A equals to R into O. A equals to R into rho. Okay. Now if you put all the values, it was shown that rho total electron density for three protons total electron density, that comes to be 0.4146 or 0.138, like that. Okay. So from that you can say only 14% of electron density are present in hydrogen. So most of the electron density that are present on carbon atom. Okay, I have also discussed about that. That most of the electron density in methyl radical is residing on carbon atom. Now there is a discussion on whether the geometry of methyl radical, they are pyramidal or planar. Okay, so I am writing two geometries. So actual question is this two orbital same? No. This is why this is not same, because this is pure p orbital and this is sp3 orbital. So how can you distinguish? First of all, you need to have C13, okay, to distinguish that, because hydrogen's interaction will be different. Okay. So if pure p orbital, the lone pair is on pure p orbital, then if in your ESR you will not see any signal. Why? Because in, just like I have said, that their interaction with the nucleus will not happen. Why not happen? Because p orbital has a node at the nucleus. But for CH3 dot radical in this geometry, tetrahedral geometry or pyramidal geometry, you can see this is on sp3 orbital which has 25% of s character. Since it has a 25% s character, so you are expected to see some signal. But actually, what happened when you are taking this ESS spectra, you will see very faint signal, which supports that this could be the structure. Okay, and then it was shown that if different nuclei are present, then with different values of nuclear spin, then number of hyperfine lines will be given by multiplication of I of 2n I plus 1. Okay, so this was the topics that I have discussed about in the last week about ESS spectroscopy. Okay, so now we are moving to another spectroscopic technique. So electronic spectroscopy technique. So this is the new spectroscopy which is known as electronic spectroscopy. Very interesting kind of spectroscopy this technique this is. Now I can use it. Yeah. So this is called electronic spectroscopy. Okay. So for every system, they if they interact with light, they will show electronic transition. Okay, electronic transition is possible for every system. But before beginning of this electronic spectroscopy, there was some discussion on the creation of molecular orbital from atomic orbital. Okay, so this was the discussion that how molecular orbitals are created from linear combination of atomic orbital. Many of you have learned about this. That is called LCO principle, right? Which is known as linear combination of atomic orbitals. Okay, suppose I have one s orbital, okay, and I have another s orbital. This will give me like this. Okay, this is linear combination. Okay, phi 1s, phi 1s. This will give psi 1s. Okay, if they have combined, uh, their overlap is like this. Okay, and if opposite phases are overlapping, then this will also create that phi minus phi. So phi, this is 1 minus this is 1. So there could be possible that electron densities are like that. Okay, so they will. This is called bonding orbital. This is called anti-bonding orbital. Okay, just like S, P can also do the same thing. So from here, you know what is the concept of bonding and anti-bonding orbital. If two phases are the same and they are overlapping, then you will create anti-bonding orbital, and if they are of opposite phase and overlap, they will create anti-bonding orbital. Okay. Next, there was a discussion on Gerade and ungerade symmetry. Okay, so if for some orbital, if it has a center of symmetry, then this orbital is designated at Gerade. Okay, G. And if it has no symmetry, then its name is written as like this, which is called ungerade. U. Okay, so Gerade and ungerade, these two are the symbols to designate whether this orbital, molecular orbital that is created, is actually moving, is actually why what with respect to the center of symmetry. Okay, Now combination of p orbital, it can create either sigma bond and pi bond. Okay. So suppose this is my p orbital, one p orbital like this. This is the molecular axis. Suppose it is a z axis. This is a z axis. Another will be like this. So this is plus, this is minus, this is minus, this is plus, like this. So this will create like this. This overlap will create feed on my drawing. Yes, this is plus, plus, this is minus. Okay. So if they are overlapping in the same direction like p orbital, so they will create more electrodensity here. So this is a sigma bond or p orbital. Okay. This is a sigma bond. Now, if p bonds are overlapping parallel to the c axis, that is the molecular axis. Suppose this is plus, this is minus, this is plus, this is minus. So it will see that here electron density will be plus, and here this will be minus. So this is another kind of overlap, and this will actually create pi bond. Okay. So this is the principle for preparation of all this, of how pi bonds are created, how sigma bonds are created. Okay. So discuss about that. Okay. Now, MO diagram of oxygen and paramagnetic nature of oxygen. It was very much interesting thing. So for oxygen, now suppose I'm doing it here. If you understand this one, you will understand everything. Okay. So this is your energy axis. Okay. So oxygen. So you know oxygen's electronic configuration. Oh, oxygen's electronic configuration 1s2, 2s2, 2p, 4. 1s2, 2s2, 2p4. 8 electrons will be there. So this is one oxygen. 1s2, 2s2, 2p4. So here one oxygen atom, here another oxygen atom. Both will have the same energy? Yes. Why I am writing these oxygen atoms on the both side? Because I want to see how oxygen molecule will look like. So that's why for oxygen molecule we need two oxygen atoms. Okay. So for that I am writing two oxygen atoms on this like this. Okay. So this is one is, this is another one is. Now this is 2s, there is 2s. There is 2p, there is 2p. 2p xyz, there is also 2p xyz. These nothing are nothing but oxygen. Okay. So for oxygen, I am just drawing it that how it actually looks like. Okay. So what I have said that when two atomic orbitals combine, they give molecular orbital. So when two molecular orbitals linear combination, either they can add or they can subtract. If they add, they will create orbital which has lower in energy, which is known as bonding orbital. And is this sigma or pi? This is sigma orbital because the s orbitals are overlapping. Okay, sigma 1s. This is also known as sigma star 1s. Okay, so this is the bonding MO of 1s and this is the anti-bonding MO of 1s. Similarly, for 2s, like this. So this is sigma 2s and this is sigma star 2s. Same for 1 and 2.
So orbitals, I have filled it that two s orbitals are overlapping. They will create one bonding orbital and one antibonding. Now for 2p case, so the orbital of p which is in the molecular axis, they will create a sigma bond. I have shown here like this. Okay, so one orbital will be there, another orbital will be there. Now what about two pi orbitals? They will also overlap, but they will create pi bond. Okay, so I should use another color to distinguish that. So these are pi orbitals. Pi pxy, pi 2p x and y. This is pi star 2p x py. Okay, so these are sigma orbitals and pi orbital. So this will be sigma 2pz. Suppose this is sigma star 2pz. Fine. So these are the this is the molecular orbital picture, and it is not complete because I have not put the electron. So now I am putting electrons here, one and two. Sorry, two electrons. One is two is two p four. Just like that. Here I am just putting again it. Okay. So just put the electrons over here. One, two, four electrons. So I have placed four. Two and two, four electrons. I have placed four. Here four and four, eight. One, two, three, four, five, six. And heat will contain one, it will contain one. Okay, so this is most possible way. Why they are not putting in the same orbitals? Because in that case, if also if two orbitals are there, so singly each of orbital occupation will be much more favored compared to a full occupation and a vacant orbital. Okay, so in that case, it will see like this. So in the highest orbital, we can see that there will be pi star 2p 2px 2py. This will contain two electrons, one each. Okay, so this will be responsible solely for the paramagnetic nature of oxygen, because a paramagnetic compound is proved by presence of unpaired electron. So oxygen has unpaired electrons, so oxygen is paramagnetic in nature. Also it signifies something else, that for oxygen two unpaired electron has spin same. So if you get the spin multiplicity 2s plus 1, 2s plus 1, if you get this will be 2 plus 1, it will be 3. So triplet state. Okay. So ground oxygen is triplet. Oxygen in the ground state is actually triplet. Okay. Now the term symbols calculation, molecular term symbol calculation, and what are the rules to calculate this molecular term symbol? There it is what is discussed very good by Professor Shan Bakchi, and I will also discuss that. But I will do for this boron. It is a very complicated system. So if you will be able to do it for complicated system, then you will be able to do it for simple systems. Okay. Then there was a discussion on the ground state term for hydrogen and bromine, hydrogen and boron. Okay, and if you have seen that it comes as 1 sigma, and for boron it comes as 3 sigma. How this is coming for boron I will show you. Okay, so if you can understand from this, you can also find this for same thing like He2, Li2, Be2 like this, and if you can check it with the results, or they're also given in Angel's book, Angel's Red book. So if you can want to check, you after learning this, you can check also. Okay, so this was the lecture of lecture 57. Okay, so lecture 58 actually tells what is known as Born open number approximation. I have told it about in the very beginning of this course. What is Born open number approximation? Born open number approximation tells that the total wave function you can take it as electrons and nucleus wave function separately. Okay, the electrons total wave function you can take as a difference of different wave functions of electronic and nuclear wave function. Okay, and then they are shown that the vibrational level change gives quad structure, but rotational levels actually give fine structure. Okay, and the appearance of band upon this name is V prime progression is given. So progression is given because that means they are coming from the same state, same V double prime, but different V double prime, but same V prime. So these will be called V prime progression. Okay, so like every is if you get this line, so if you get lines like this, this which corresponds to 3 to 1, 4 to 1, 5 to 1. So this one is common in everything because it is coming to the final same state. So this is called progression in 1, just like progression in V1. Okay. Then the change of the excited state potential energy curve with respect to ground state for change of R equilibrium. 4 cases were discussed. So let me check how much space I have. Okay, yeah. So I have enough space here. So 4 cases were possible. First case is R equilibrium. Okay, so this is one case. Here R equilibrium of the ground state and the excited state is same. Okay, so maximum transition will be 0 0 transition. So if you plot this, so 0 0 will have maximum intensity, and then 0 1 0 2 like that. Okay, okay. So in this case, you see there is no change in the equilibrium bond length. Fine. Now suppose this is your ground state, this is your excited state. So here R equilibrium is slightly higher than R equilibrium in the ground state. Okay, so don't miss the axis. I just mixed E and R. So in this absorption spectra, you see this line is very much intense, not this line. Okay, so for that, you need to consider one thing which is known as Frank-Condon principle. What does Frank-Condon principle tells you? Frank-Condon principle actually tells you that the electronic transition happens so fast that you can say that a nucleus is since it is a since nucleus is a very heavy mass, so you can consider that nucleus is actually remains fixed. Okay. So when you are going to have absorption lines here, you are expected to see this one as the highest intensity. Suppose this is 20 or 30. This will have highest intensity. The intensity will be goes on changing. Okay. So since it is following fan control zero, so 0 to 0 transition will not have. Suppose this is 0 to 0, 0 to 1, 0 to 2. Sorry, this will be 0 to 2. Okay. This will be 0 to 2. So these transitions will have, and among these 0 to 2 will have the highest intensity. Suppose what happens that this is the ground state and this is the excited state. It can also happen. So there is a decrease in the equilibrium. Okay. So this is I and this is R. And you see that this is the highest intense peak, high intensity, just like that. In the previous case, 0 to 2, plus 0 to 1, 0 to 2 highest, and intensity is changing. Okay, like that. So this is the third case. Another case will be there. Suppose this is a ground state, and this is excited state is very much shifted. Okay. So some point of time you will reach the excited state, but this will below continuum. Okay. Here up to here this is highest value, and after this is a continuum. So the molecule actually dissociates. So you in spectra you will look like this increasing, and then this will be like this. Okay, there will be a continuum because you have changed it so much that it goes to the dissociation limit. So the molecule in the excited state actually it will dissociate. So these four are the possibilities of the change of this excited state potential energy curve with respect to the ground state. Okay, so this was the discussing matter for lecture number 58. Next, I am moving to lecture number 59, which discuss about the dissociation of a molecule in the excited state. The same thing which I have stopped in the last discussion. That suppose this is my energy axis and this is my E and this is R. So suppose this is my ground state. This is my excited state. Okay. So what is this? Suppose this is for 0 to 0 transition. I should use another ink. So suppose this is 0 to 0 transition. This is the dissociation energy. You know it. Suppose for this for excited state. And this is the 0 point energy. This is the dissociation energy for the ground state. D0 prime. And this is the energy need to provide Ex. Okay. Excitation energy. This energy you need to provide to give it to the bring it to the excited state. Right. So whenever you get the species in the excited state, from that species you can easily calculate this D0 prime. Okay. And from that exchange energy calculation also can be done. What is exchange energy? Exchange energy, whenever if you know your molecule will be broken, if you give some this much of energy is sufficient, okay, to break your molecule. Okay, so if some amount of energy is needed, so and if you are giving much energy, so what will be, this energy will be dissipated. So this is called excess energy. So higher value of vibrational quantum number actually considering the dissociation limit. So what should be the maximum value of quantum number? Okay, so we know from vibrational spectroscopy calculation delta nu bar, I can write nu bar E into 1 minus 2 chi E into B plus 1. Remember, this is just delta nu bar. That means difference between two nu bar states. Okay. Okay, so what should be the maximum value? V equals to V max. You know, at the recession limit, what will happen? Your delta nu bar will be equal to 0. So from that, what you get? Nu e prime into 1 minus 2 chi e into V max plus 1. This is 0. So either this part is 0 or this part is 0. So this will give V max equals to 1 by 2 chi e minus 1. This is the formula for V max we are going to get. So this is the value of V max you are going to get if you consider this one. Okay. Now your chi e has the order of 10 to the power minus 2 order. So V max maximum have a value of nearly 50. The highest vibrational quantum number which is possible for this molecule is almost 50. Then there was a discussion on rotational fine structure. Oh, just a minute. Okay, so excited state dissociation energy can also be calculated using one plot, which is a plot of G versus B, that how this G is changing, or so, and then it was shown that it is not changing linearly, it is actually in the high value of V, it is actually this thing, okay. So this is known as Birgi-Sponner's plot, okay, Birgi-Sponner's plot. So from that, you can calculate the dissociation energy of the excited state if you are getting this area under the curve, okay. And then rotational fine structure was discussed, and also the pre-dissociation condition was arrived. What is pre-dissociation condition? Suppose this is my system, this is my ground state, and the excited state comes like this one. Okay. So getting some energy in the before going to the excited state, this is actually getting dissociated. So this is called pre-dissociation condition. Okay. So before crossing this, it is actually getting dissociated. So this is the measure for lecture number 59, where Professor Sandberg has discussed about the dissociation energy of the molecules and how to calculate this dissociation energy for excited state and for the ground state, and also discussion about Birges-Sponner's plot, and also rotational fine structure was discussed. In the next lecture, there was a discussion of Laporte and spin selection rule for polyatomic molecules. Okay, so what are these? Actually, what Born Oppenheimer have told, that psi total I can write as psi nuclear into psi electronic, right? So transition moment integral, if you go through transition moment integral, you can see your what will be there, psi phi total, psi electronic final state, psi nuclear final state, because I can write total psi as psi neutral, psi electronic, and psi nuclear. Just like mu, I can write mu electronic plus mu nuclear, but they are additive. Okay, and here mu electron psi electronic initial, psi nuclear. This is initial. Okay, now from here you can just change the terms, and from one case you will get a term like psi nuclear. So if you go through calculation, psi nuclear, one term arises like psi nuclear as psi nuclear, and this is nothing but Frank Condon factor. Okay, so this actually relates the position of this overlap of this nuclear wave function for this initial and final stage. Okay, and now from this electronic point of view, you will get, if you consider space and spin, you will see that psi f space, psi, if you consider this total wave function of electronic wave function can be divided into spin and space, if you write it like this, space mu electronic, this is psi I space. Okay, so this is the spatial part, and spin part will be there psi star f. Oh, sorry, I am writing in bracket notation. I said not supposed to use space. Star. Sorry, I'm supposed to use star. Okay. So this is psi f spin, psi f, psi I spin. So if you divide it, this electronic wave function into two categories, one is space and another is spin, you will see that this will be the condition, this will arise. Now this comes to your spin selection rule, because you know to have to select electronic transition to happen, for electron transition to happen, your best condition is that the transition moment integral should be non-zero. So spin, this condition should first satisfy that the spin will be, I mean, if 2 delta s will be always 0. Okay, that means the transition from singlet to singlet is allowed because the wave functions will match and it will give you 0, non-zero value. But if this wave function is different, this will give you not 0 value. Okay, so since the orthonormal nature of this spin wave function, so only allowed transitions are from singlet to singlet and triplet to triplet. This is giving you spin selection rule, and from that you will see that mu l el is having u symmetry. Okay, the mu el, that is the electronic dipole moment, will have mu u symmetry. So these two, this multiplication will also need to have u symmetry to make this total part g symmetry, because you know what I have discussed, that to for a wave function to be totally to be non-zero, this part, every part will be totally symmetric. So d g will be totally symmetric. Now in between them, it is u. Okay, so this multiplication of this and this should be u, and u it comes only when g into u will be u into g equals to u. Only under this condition, two multiplication of these two wave functions will be u. Okay, and this, for this to happen, these two will have different wave functions parity. Okay, if size in final stage has parity of g, then initial state must have the parity of u, and this is known as, so the transition only happen from g to u and u to g state, and this is known as Laporta selection rule. This is known as Laporte selection rule. Okay, so this is the concept behind Laporte selection rule. So two kinds of selection rules you have seen here. One is spin selection rule, which tells you that the transition between same spin states are possible only. And Laporte selection rule, sorry, Laporte selection rule tells you the transition between two wave functions of different symmetries are only allowed, or different parity are only allowed. Okay, and this Laporte selection rule is explaining why octahedral complexes actually are weakly colored. So if you see octahedral geometry, 5d orbitals are there, and since it is simple symmetry molecule, you know this is T2G and this is EG. Okay, and so this parity is same. So this rule is not following here. So this is Laporte forbidden. Okay. So for this case, this Laporte forbidden rule is applicable, but for tetrahedral complexes, since they don't have any kind of G or U parity, so they are actually intensely colored. So this is actually observed when you are seeing the potassium. Sorry. So if you see that octahedral complex, octahedral dimensional complex, this will be very weakly colored, but tetrahedral complex are intensely colored. But there could be some exception when there is a breakage of parity, whenever one orbital is actually coupling with another orbital which actually breaks the parity, then this transition become allowed and this octator complex will get some color. Okay, but there is another concept of LMCT, MLCT. Okay, so this is MMCT is also there, but also there will be MLCT. Okay, so what was I talking? Yeah, KMNO4. So KMNO4 like the adult potassium dichromate, they are intensely colored. Why are intensely colored? Because from oxide, since manganese is in the D0 state, manganese plus 7, it is a D0 state. So oxide will actually push electron density towards manganese. Okay, since they will push electron density to manganese, then the electron density pole will actually increase the magnetic dipole. Okay, so it will increase the transition dipole. Since transition dipole increases, so the intensity increases, because in the transition moment integral expression you are seeing the term actually appearing as transition dipole. Okay, so since transition dipole increasing, so intensity will increase. And the intensity will be proportional to the intensity of transition, will be proportional to transition moment integral square. Okay, and another thing will be there, that MLCT. What is MLCT? MLCT is nothing but metal to ligand charge transfer. When the ligand is devoid of any kind of charge, then metal have much more electron density, so it can donate its electron. It is actually occur in case of organic system like Fe3, like kind of system. Okay, and it was shown that for C double bond C, the transition from pi to pi star C is happening, but for pi n to pi star transition, it happens for CO because it has lone pair of electron. Okay, so if I designate orbitals, this is sigma, this is pi, this is pi star, this is sigma star. These are the designation of the orbitals that are present. This is sigma, this is pi, this is n, this is pi star, and this is sigma star. Okay, so this is one transition, sigma to sigma star. This is one transition, pi to pi star. Another two transitions could be this and this is. But you know, this n to pi star transition, this is actually symmetry forbidden transition. Okay, so very intensity will very weak for this kind of transition, symmetry forbidden transition. Okay, since it is symmetry forbidden transition, so intensity will be very weak, mainly for n to pi star transition. This will be very much weak with compared to pi to pi star transition. Okay, so this was the discussion for lecture number 60, and in the last lecture, Professor Bakshi has explained that shifting of this electron transition to a longer wavelength will increase in conjugation. Okay, okay. So he wants to say that if you are increasing conjugation, if you support consider it as a particle in a box system, then you see as you are increasing the chain length or you are increasing the conjugation, the difference between this HOMO and LUMO is actually decreasing, and it will increase actually wavelength will be increased. Okay, so if you consider it as a particle in a box model, then the energy, you know, particle in a box, n square h square by 8 ml square. Okay, so suppose in this system there is 10 pi electrons, so you can consider this for 5. Okay, like this. So from 5 to 6 the transition will happen. If you put these values, you will get what? This will get n, suppose n carbon atoms are there, so n by 2 will be the highest, n by 2 plus 1 will be the LUMO. If you get it, it will get n plus 1 h square by 8 ml square. This will be your delta E, and from delta E you can calculate delta lambda or lambda. What should be the wavelength of light associated with that transition? Okay. So, and so this is written here that using particle in the box model, how increasing conjugation actually increases, how increase in conjugation actually absorption wavelength increase happens. Okay. Now there was a discussion on the fate of molecule in the excited state. So whenever I have some excited state, suppose this is my ground state, okay, it is generally it is represented as S0 state, okay, S0 state. So it is going to some excited state. Suppose it is going to this state S1, okay. So different photophysical processes can happen. Either it can do photochemical reaction, it can do photochemical reaction, which is comes under the category of photochemistry, or it can have photophysical processes. So this process is called absorption, and it occurs in a femtosecond time scale. Okay, so absorption actually occurs in a femtosecond time scale, 10 to the power minus 15 seconds. You can imagine how much fast it is. Okay, now electron from this S1 state, it actually there are some vibrational levels are there. So from there will be a vibrational cooling. So that will be better if I take another slide to discuss only this one. So this is actually known as Jablonski diagram. Okay. So if you take any fluorescence spectroscopy book, you will you are supposed to see this Jablonski diagram. Suppose this is my S0 state. Okay. So there are vibrational levels associated with that. Ignore my drawing. These are all the straight lines. Okay. Okay. And these are, suppose this is S1 state. Okay. So S2 states will be there. So suppose for this S1 state, these are the vibrational levels. So what are the rotational levels? Rotational levels are actually accompanying these vibrational levels. These small levels what I am drawing now, it is nothing but vibrational level. Okay. So whenever an absorption occurs, absorption actually occurs in a femtosecond time scale. Suppose from this is happening from, yeah, it's become too difficult to draw straight line here. Yeah, suppose it is setting here. This is a straight line, okay? Let's consider this as a straight line. So from that, it is coming cool vibrational cooling, and it will coming here. This is known as vibrational cooling. Okay, and this process is known as absorption. What is the time scale for vibrational cooling? What is the time scale for absorption? This is femtosecond. What is this? This is femtosecond to picosecond. Okay. Under that condition, what will go? It will come. The molecule in the excited fast molecule is here. From here, it is undergoing vibrational cooling. It is coming here. Okay. So this is called vibrational cooling. Now, from here, it can come back to the ground state radiatively. Okay. This is known as fluorescence. And it occurs in nanosecond time scale. Okay. So this is known as fluorescence. What is fluorescence? Whenever you are exciting some molecule, it is after vibrational cooling, it is coming to the lowest vibrational state of the excited state. Okay, you see that whenever I have drawn fluorescence, the molecule is in the lowest vibrational level of the excited state, and always this emission will always happen from lowest vibrational level of the excited state, and this is known as Casas rule. Okay. Casaubon states that the emission will always happen from the lowest vibrational level of the first excited of the higher excited state. This is called fluorescence. Okay, so if molecule I have excited this molecule to the some state like S2, okay. So from S2 it will come here, okay. So with this I am drawing another level which is also known as triplet state. These are terrible drawings. So forgive me about this drawing because I'm not too much used to with this virtual board. Okay, this is T1 state. Okay, now to have this. Okay, yeah. So whenever there is this here, it is whenever suppose I am setting it here. So from here it can come here via a non-radiative process. Okay. So whenever there is a transformation from between two states of same spin multiplicity, suppose here S1 and S2, you can see they have same spin multiplicity. So this is called internal conversion. Okay. So whenever there is a transfer from between the states of same spin multiplicity, this is called as internal conversion. So from this S1, the molecule can either go non-radiatively to T1. Okay. This is actually not happens like this. There are also vibrational levels, and this overlap actually pushes this to this level. Okay, and then vibrational cooling happens. So this is known as inter-system crossing. Okay, so inter-system crossing means the molecule will go from a state of a spin multiplicity to another state with different spin multiplicity. Suppose it is in S1, it is going to T1. This is an internal inter-system crossing. Also, it is in T1 and it is going to S1. This is also an inter-system crossing. Okay. So from this T1, there is some vibrational cooling here, and from here, this can come back to the ground state radiatively. Ground state radiatively. So this is known as phosphorescence. So this happens in the microsecond to second scale. Okay, phosphorescence actually happens from T1 state to S0 state, and it happens in the microsecond to second scale. So these are the different photophysical processes that are involved whenever molecule is in the excited state. Okay, another thing can be happen that sometimes if S1 and T1 are close, if S1 and T1 are close, so what happened that molecules from suppose S1 they are coming to T1 and getting back. If this is coming to T1 and it is again getting back to S1 and then it is giving fluorescence. Understand? So molecule is in the excited state. This is coming to the T1 state, S1 to T1. Then it is again going to T1 to S1 and then this is giving fluorescence. Because whenever it is coming back to S1 state and from S1 state it will only give fluorescence. So this fluorescence is known as delayed fluorescence. Okay. So these are all the photophysical process that actually happens in the molecule is in the excited state. Okay, and this diagram is known as the diagram I have shown you is known as this is known as Jablonski diagram. This diagram is if you understand this diagram, you will understand the half of this photochemistry or spectroscopy. Okay, so uh, Jablonski diagram is actually the introduction to fluorescence spectroscopy, a new branch of spectroscopy which is known as fluorescence spectroscopy. Okay, and so processes I have shown you that which are radiative processes. What are the radiative processes? The processes which you will get light. Okay, so molecule when coming back to the excited state to the ground state, they will emit light. If they are not emitting light, they are coming at heat or other means, then they will called as non-radiative processes. Okay. So these are all the topics that was discussed by Professor San Bakchi about this electronic spectroscopy. Now I am moving to some questions. So this is my first question. Which of the following statement is correct? First option is it has two unpaired electron. It has homo of oxygen is pi 2p star g, pi star 2pg. Homo of oxygen is sigma 2pg, and it has no unpaired electron. Four options are there. So you find you will find this answer in lecture number 57. That in the MO diagram of oxygen, I have shown you the MO diagram of oxygen. The HOMO, you can see if I write the if I write orbital MO configuration, okay. So suppose you know, okay, I am drawing it again. This is 1s, this is 2s, this is 2p. Okay. So for short, don't I have shown details sometimes before. So this will give you 1s. Okay, so I designate this is as sigma 1 sigma. This is 2 sigma, 1 sigma, it is a 1 sigma star. This is 2 sigma, this is 2 sigma star, this is 3 sigma, this is 1 pi, this is also 1 pi, this is 1 pi stars, 1 pi stars, and this is 3 sigma star. So if I designate this, you know oxygen has total 16 electron. If you put this like this, 1 each, okay? So these are total 16 electrons. So if I write this configuration, you do it on your own, you will get 1 sigma G. It is on. It will have G configuration. It 1 sigma G2, 1 sigma star U. Sigma star will have U configuration 2, 2 sigma G2, 2 sigma star U2, 3 sigma G2, 1 pi U2, 1 pi U2. Okay, 2 pi's, 1 pi's will you will write like this, and then pi will be U symmetry, and then 1 pi star G1, 1 pi star G1. This is the configuration of oxygen. If you whenever you have done this, you will just calculate the number of electrons 2, 2, 2, 2, 8, 10, 12, 14, 15, and 16. Okay, so I have 10, 16 electrons. Now, a question is that which of the following statement is correct? First question is oxygen has two unpaired electrons. Correct? This is correct. The first option, that oxygen has two unpaired electrons. This is correct. Homo of oxygen is pi star 2pg. Pi star 2pg, yes. Why? Because you see, this is pi star and g, and this is the 2p orbital of oxygen. So this is pi star 2pg. Homo of oxygen is not sigma. Okay, and it has no unpaired electron. This is also not possible. So answer is it has two unpaired electron and its HOMO will be pi star 2pg. Okay, so this is the answer. So moving to the next question, I have promised that I will show you calculation of the ground state term for B2. So B2 you need to write first electronic configuration. So I have written for clarity the electronic configuration, and from that I would extend it. So like that, 1 sigma G2, 1 sigma star U2, 2 sigma G2, 2 sigma star U2, 1 pi U1 and 1 pi U1. Okay, okay, just okay, you see it, then no problem. Okay, so you see that whenever you are going to calculate your term symbol, you need to consider what is the total ml and total ms. Okay, since your highest orbital is pi orbital, so pi orbital means two pi orbitals are there, so their ml is plus minus 1 and s is plus minus half. So three combinations are possible for ml, capital ml. This could be 2 0 2 minus 2. Okay, so this 2 will either give 2, this will give 0, this will give minus 2, and s equals to plus half and minus half. This will be possible in ms is plus half plus half plus 1. This is ms equals to 0 and ms equals to minus 1. Okay, just coming. Yeah, sorry for the delay. Okay. So I was discussing that audible. Yeah. So so ML values possible are 2, 0, and minus 2. MS value is possible plus 1, 0, and minus 1. So you can see 9 combinations are possible. Okay. So ML and MS. Okay. So 9 combinations possible, 2, 0, minus 2. This is plus 1, 0, minus 1. So I'm writing like 2 plus 1. Okay, so this is 2 for ML, MS 2 plus 1. 0 plus 1 minus 2 plus 1. This is first I'm writing spin, sorry, L. So 2, 0. This is 0, 0. This is minus 2, 0. And here 2 minus 1, 0 minus 1. And here minus 2 minus 1. Okay. Now you just understand that ms equals to plus 1 or minus 1. This means two electron have same spin, right? And ml equal to plus 2 minus 2. That means two electron have same ml, right? So according to Pauli's exclusion principle, uh, according to Pauli's exclusion principle, same ml and same ms, these are not possible. Okay, all four quantum numbers cannot be same. So first case here, now I am taking this green one. So for first case, ml equal to plus 2, which means two electrons have same ml, and ms equals to plus 1. That means you can write here that ms equals to plus 1 is two electrons have same spin. So same ml, same spin. So it will not be considered. Just like minus 2 plus 1. This will have same spin, same ml, not considered. 0 plus 1. Same spin but different ml. It can be considered. Plus 2, 0. These have different ms but different same ml. Same ml but different ms. Okay, it can be considered. Now 0, 0. That means these will have different ml, different ms. It will be considered. Minus 2, 0. Same ml, different ms. It can be considered. Here 2 minus 1. Same ml, same ms. Cannot be considered. Okay, 2 minus 1. You write here. This is 2 here minus 1. So it can be considered. Cannot be considered. Again, uh, so here ml equal 0 minus 1. That means ml is not same, spin is same. You can be considered it. Minus 2 minus 1 you cannot consider because these two have same spin and same ml. So only 5 combinations are possible. So possible ml values is 0, this 3 0, and 2 minus 2 twos. Okay. So 2 plus 2 minus 2, 1 plus 2 and 1 minus 2. Okay, you can see here this 3 have 0 ml and here minus 2 ml. Okay. So here you see these two will have same spin. Okay. So and ms, so 0. Okay. So for clarification I just now the combinations are ml comma ms. Okay. So combinations possible 0 plus 1. So equal to I will write it right there. Yeah. ml ms. 0 plus 1, 0 0, 0 minus 1, 2 0, minus 2 0. These fives are possible. Okay. Now you know this electronic term, how can it write in 2s plus 1 mod ml. Okay. So here you see what is this 2s plus 1? This is 1. And ml is, sorry. So I need to make another part here. This 2s plus 1. Okay. So here you see just ms values. What is 2s plus 1? 3. 0. Oh, sorry. 3, 1. 1. So this is minus 1. So ms 2s plus 1, it will be 3 mod. Okay. This is 1. This is 1. Fine. Now the symbols will be, if ml is 0, then it will be sigma state. So 3 sigma. Okay. Here this is 0 0. Okay. 0, that means sigma. And here this is 1. So 1 sigma. Here this is 3 and this is 0 sigma. So same states are there. 3 sigma. Here ml is 1. 2 means sigma delta, sigma pi delta. So naming are like that: 0 1 2 3, like that. So it will be sigma pi delta phi, like that. So this will become 1 delta. Here this will be 1, so a 1, so 2, this will become mod. So mod 2, this will be again 1 delta. So 2 1 delta state, 2 3 sigma state. So 3 states are possible actually. Among these, 1 sigma, 3 sigma, and 1 delta. These three are the possible states for ground state of B2 molecule. Okay. Now you have to find among these three states which one will be the ground state. So Hund's rule states that maximum spin multiplicity will be the ground state. Okay. So this will be the ground state. So 3 sigma is the ground state of boron. So your answer is like this. Answer is 3 sigma. I think you have understood that. Yes. So this is the answer. Now, third question. Frank Condon's principle assumes that R equilibrium of ground state is equivalent to R equals to R equilibrium of excited state, or which one is greater. Okay. So Frank Condon principle states what I have so told you, that what Frank Condon principle states. Frank Condon principle actually states that the electronic transitions is always vertical, that is, in which there is no change in the bond length. Okay. That means nuclei are almost fixed. If you understand the physical picture, this is a bond. Okay. So Frank Condon's principle states that nuclei, this electron transition happens so fast that nuclei are almost fixed. That means internuclear separation is not changing. So R is actually not changing. So it can find in reference number 58 that according to Frank Condon principle, during electron transition, nuclei remains static, that is the transition is vertical. Hence, equilibrium bond length is not changing. So ground state bond length and excited state bond length, they are equal according to Frank Condon principle. So this is the answer. Okay. Next, this is a straightforward question. According to Laporte selection rule, for centrosymmetric molecule, which of the transitions are allowed? So this you can find in reference of 60, reference lecture number 60, that Laporte selection rule states that for an allowed transition, the parity of the state must change. I have shown you that the ref function looks like this: phi space of final state, mu of L, psi space of the initial state. And you know this has U parity. Okay. So to electron happen, for electron transition to happen, these two products the product of this size space of final and size space of initial, this will have U parity, need to have U parity so that this product will be U parity. Okay, what I mean to say that this is U parity, you fixed by U parity. Okay, so to make it non-zero, this total one need to be G parity. So from U parity, how can you get G parity? If there is some multiplication with U. Okay, so if there is, you have to have some multiplication with U, then you know that G into G and U into U cannot give you U. They are not equals to U. So if two states have the same parity, then they will not give you U. Unless they are of different parity, they will give you U. So the transition will happen from only G to U and U to G. Okay, the all other transitions from U to U and G to G are not possible for centrosymmetric molecule. So this is the answer. Next question. So intense violet color of MnO4 minus is due to which one? So I have discussed that MnO4 minus in this Mn in the +7 oxidation state. Okay, D0 system. So it has a deficiency of electrons. Whenever this is attached to some oxide like this, so I don't know if I am writing it right or wrong. Like if I remember that this is the structure for MnO4 minus, so manganese will have electron density from this oxygen atom. Okay, so since we will have electron density from this oxygen atom, so the length or so the electron distribution over this system will increase. Okay, since it will increase, so it will increase mu. That is the transition dipole moment. So because transition dipole moment, you know, dipole moment is charge zero distance. So if it is over long distance, then this distance will increase. So your mu will increase. Okay, mu increases. Mu increase means there will be intensity increase. Hence, there is intense violet color that is observed for permanganate. Okay, and this is known due to this, and this intense violet color is, and this intense color is actually due to charge transfer. So charge transfer is happening from where? This, from the oxygen to manganese. What is oxygen here? Oxygen here is nothing but ligand. Okay, and this is the metal. So this is nothing but an example of ligand to metal charge transfer. So this is known as LMCT. This is also known as LMCT. Okay, so you can find this answer in lecture number 60 also, that Mn7 plus is a D0 system, hence transfer of electron density from oxygen to Mn is not possible. So due to this transfer of electron, the transition is possible, and due to this transfer of electron, the transition dipole moment increases, which in turn increases the intensity of transition. Hence, intense violet color is observed for permanganate, and this is an example of ligand to metal charge transfer. What I have said here. So this is the answer. So next question, among n to pi star and pi to pi star transition of carbonyl, identify the correct statement. Okay. So question is, just I am drawing it again. Yeah. So this is sigma, this is pi, this is n, this is pi star, this is sigma star. Okay. So sigma to sigma star I have not included here. So for carbonyl, this transition and this transition, which one will be the stronger, and which one will be the and symmetry allowed or symmetry forbidden. Okay, so you know that n to pi star transition, n to pi star is actually symmetry forbidden, but pi to pi star is symmetry allowed. Why? Because you have seen that phi, if phi is u and the pi star will be g, and u to g is u allowed, you know. N to pi star is actually symmetry forbidden. It is here written, yes, n to pi star is symmetry forbidden. Here is right. Both symmetry allowed is not correct. But now you have to find which one is stronger. Since this is symmetry forbidden, so this will be weaker in intensity. So pi and pi star will be stronger in intensity. Okay. So you can find this also in lecture number 60. That for carbonyl, n to pi star is symmetry forbidden transition, and also pi to pi star is more stronger than n to pi star. So this is the answer. Pi to pi star is stronger, and n to pi star is symmetry forbidden. Next question, which of the following is an intersystem crossing? You know, if can find this in lecture reference in lecture number X61, and you will it will be lecture 61th lecture. So intersystem crossing actually refers to transition between two states of different spin multiplicity. You can now read from different name intersystem crossing between, that means crossing between two different systems. Okay. So the transition from S1 to T1 is an intersystem crossing, or Tn to Sn, this is also an intersystem crossing. So T1 to S1 or anything. Okay. So any from Sn to Tn or Tn to Sn, this is an example of intersystem crossing. Here you know this is S0 to S1. So if you know this is nothing but absorption, ground state to excited state. Okay, S0 to S2, this is also an absorption. T1 to T2, this is also absorption. But S1 to T1, this is nothing but intersystem crossing. Okay, so answer is this one. Now, time scale for electronic absorption of ground state to first excited state is, so it is asking about that time scale for electronic absorption. Okay, so I have gave you this answer that absorption occur in a time scale of 10 to the power minus 15 second, which is nothing but a femtosecond time scale. Okay, so you can find this also in lecture number 61 that absorption occurs in time scale of 10 to the power minus 15 second. Okay, so this is the answer. Okay, so if the minimum of the Morse potential of the excited state is at a larger R than the ground state, the rotational constant of the excited state will be what? So, larger R means R equilibrium in the excited state is greater than R equilibrium in the ground state. This is the question that is asked here. Okay, ground state. Okay, so in excited state, the R equilibrium is higher than the ground state, slightly higher, larger R than the ground state. So, what should be the change in the rotational constant? You know, whenever you have learned that rotational constant, you know it has a inverse dependency on I. I, what is I? I is moment of inertia. And you know, moment of inertia is directly proportional to mu r square. So it is proportional to r square. So, you know, B has a proportional to 1 by r square. Okay. So, B, since B is proportional to 1 by r square, so if you increase r, what will happen? B will decrease, right? So in the excited state, you know, you have in the excited state you have R equilibrium is higher than the ground state. Okay. So since R equilibrium is higher in the excited state, so what will happen that in the excited state B will be lower. So B of excited state is lower than B of ground state. Understand the concept? It's just a conceptual question. That whenever if you have excited state in the high excited state, the R is higher than the ground state. So what will happen? So it will happen that since R is increasing and you know that rotational constant is inversely proportional to R, so if R is increasing, rotational constant will decrease. So what will be there? The question is the rotational constant of the excited state is smaller than the rotational constant of the ground state. Is this correct? Larger than the rotational constant of the ground state? No. Equal? No. Can be either smaller or longer? No. So whenever you are just doing a MCQ, you just also need to see all other options. Okay. So minimum Morse potential function increases to larger R, which means rotational constant decreases. Okay, in the excited state, as B is inversely proportional to R. So the answer is B is inversely proportional is smaller than the rotational constant of the ground state. Okay, octahedral complexes are fluidly colored due to what? This is a question. Okay, octahedral complexes. I am just giving you idea. I think some of you have got this idea of why octahedral complexes are being colored. So first of all, I'm just going back calculation. I'm doing back calculation. Okay. So octahedral complex means centrosymmetry, right? Not necessary, but I am just for perfect octahedra. It is its centrosymmetric molecule. So the electronic levels, suppose D levels are there. So transitions will be from T to G to EG, right? So octahedral complex will give color when there is a transition from this to this. Now you can see the both the states have G symmetry. Okay. So whether they are of singlet, this can be triplet, this can be doublet. Okay. So then transition can also possible. So spin is there is no question of spin. But if this is T2G and this is EG, so this transition is not possible. Why not possible? Because of a selection rule that G to G transition, U to U transition is not possible, which is known as Laporte selection rule. Laporte selection rule. So Laporte selection rule, what this states that transition from G to G and U to U not possible. So transition will be possible if the parity are changing. So you can find in terms of lecture number 60 that octahedral complexes are weakly colored due to forbidden of transition of from G to G and U to U. Hence the answer is Laporte selection rule. Okay, Frank Gordon spin selection rule, rotational fine structure, they are not there. Okay, last question for today, that the wavelength of fluorescence. So what is the wavelength of fluorescence? So I have told you that if this much energy levels are there, so for clarification, I'm just writing only C here and only one in the ground state. Okay, so this is absorption process, right? Absorption. So this is absorption. Now it is coming from here to here. Okay, by vibrational cooling, and this will be coming from this state. This is fluorescence. When it is fluorescence, this is S1 and this is S0 or S state. Okay, singlet to singlet. Now, why this is happening from here? Because this is a rule which is known as Casas rule. So it is following Casas rule that the transition will be happen. The emission will happen from the lowest energy vibrational state of the excited state. It is following the same thing. Now you see the delta E for absorption is greater than delta E for fluorescence. You can clearly see it that absorption is have higher energy difference because the left side energy excess is energy. Okay, left side axis is energy. So from this to this, delta E is highest from than this to this. Okay, you can clearly see it. So if absorption is higher delta E, then delta lambda for absorption will be lowest than the delta lambda of fluorescence. That means the wavelength of fluorescence will be higher than that of absorption. Okay, you got it? That the since the energy difference between for fluorescence is lower, then hence the lambda, that means the absorption, the wavelength will be higher for fluorescence. So this you can find this in lecture number 61, and I am also writing here that according to Casas rule, emission generally happens from lower level of the excited state, and for this reason the wavelength of the fluorescence is higher than that of absorption. So the greater than the absorption, fluorescence wavelength will be higher than that of absorption. So this was the discussion of about the electronic spectroscopy. So what I have taught, what I have sorry not taught, I have discussed about this course, that we have started from spectroscopy, why spectroscopy is needed. Then we have moved to rotational spectroscopy, then vibrational spectroscopy, then rotational vibrational mixed spectroscopy, and then we have moved to Raman spectroscopy. Okay, so after all the spectroscopy, we have moved to resonance spectroscopy, where we have learned about NMR spectroscopy and ESR about EPR spectroscopy, and in the end, we are learning about electronic spectroscopy. Okay, so all these spectroscopy techniques mainly are covered here. Okay, so this was a very good course, and I am very lucky to have to be a TA of this course. Okay, so this is a very last session that I am taking today. Okay, so best of luck for your future. Thank you.